So in 3.2 we talk about the graph of a function. So here's the definition of the graph of a function. And it relies on the idea that we've already defined what it means to graph an equation. The graph of an equation is all the points in the xy plane whose coordinates satisfy that equation. So here goes. The definition of the graph of a function is that it is the graph of the equation y equals f of x. So for example, let's try to graph this guy. Suppose f of x is 7 minus x squared. That's a function. You stick in x in here, you calculate this, a unique output comes out for every x that you stick in. In fact, the domain is the whole real number line. There are no radicals and there are no denominators, so the domain of this guy is negative infinity to infinity. Well, let's look at its graph. It's the graph of this equation, which we graphed earlier. I'm just going to remember what it looked like. Something like that, didn't it? I remember that it went through this point, x equals 0, y equals 7. When we calculated a table of values for this guy, we were actually calculating a table of values for this function. We were sticking in various x's and then recording what the outputs were. The domain and range of a function shows up on its graph. If I had a perfect graph, we've already decided that based on that formula there are no restrictions placed on x by that formula, so the domain is negative infinity to infinity. That means if I graph this entire curve, not just the segment that I drew here in this finite piece of paper, that every real number shows up as an x value somewhere along the curve. I'll show you what I mean. As I trace along the curve, along this way, I'll record in green the various x's that I see down there. So as I go up here on the curve, I'm not very good. Try it that way. So go along the curve this way. What's the pen that's the problem? Up here, the corresponding, I'm not good at this at all. And here are the corresponding x's. I'll record on the x-axis. If I keep going this way, I'll follow the curve over here and record in green the corresponding x values. Boy, that was a mess. But look at that. Can you see the green? That's the domain of this function. It's the whole real number line. I trust that if I kept drawing this thing, that eventually I would cover in the whole x-axis. Well, I like a challenge. Let's try to do the same thing for the y's, because the y's will show up. Hold it, too many colors. The y values along that curve will be the range. So let's try drawing the y values in blue. So I'll go along the curve, and at the same time, get my pen started, at the same time I'll record the y values on the curve just over here on the y-axis. I'll switch hands. I record these points. I end up drawing this blue part of the y-axis 2 times. Did you see that? As I drew this part of the curve in black, I drew this corresponding blue part here on the y-axis, recording the y values that my black pen was tracing out on the graph of the function. And when I did here, I traced out exactly the same y values again. That's because that function has this property that we saw when graphing it earlier, that 2 different x's can have the same y value. In fact, they will on this function. 2 different x's have the same y value. But if you look at the green part of the y-axis that you colored in, that's the range. It's the collection of all the outputs of this function. That looks like all the y's that are less or equal to 7. Or in interval notation, it's negative infinity to 7 with a bracket around the 7. I'll end this section with just one observation. That is something we already saw with lines, is that every curve has infinitely many equations. Every curve in the xy plane has infinitely many different equations. Like, for instance, this curve, y equals 7 minus x squared. There's another equation for it. I could say add x squared to both sides. Y plus x squared equals 7. Or y plus x squared minus 7 equals 0. Or 2y equals 14 minus 2x squared. Or negative y minus x squared equals negative 7. I go on for the rest of my life writing down more and more equations that all describe the same curve. But a curve is the graph of a function exactly when, among its many, many equations, there's one that looked like that, where y equals something entirely dependent on x. So the curve is the graph of a function if and only if, among its many equations, it has an equation of this form. Y equals, I'll just say, something that depends on x. Some cloud of x's there. That's if and only if it passes the vertical line test. If it passes the vertical line test, that says that the y values on that curve depend only on x. If you know x, you know y. So the y's depend on x in some way. Possibly in some way involving symbols that haven't even been invented yet. Right? If I draw this guy, there, that is the graph of a function. I'd be very surprised if there's some simple, polynomial equation or maybe even any algebraic equation for the thing that I just drew. But I'm sure that the y values on this curve depend on x's because this curve passes the vertical line test. To each x there's exactly one y. Oh, so for some x's there are no y's. That's just because the domain of this graph is from this part of the x-axis to that part of the x-axis. Its domain is just some finite interval. But the y values in this curve depend on x in some way, so that's why that's the graph of a function.